Welcome to the temperature unit. You have used the concept of temperature your entire life, but your everyday intuition is actually misleading. When you touch a metal bench on a winter day, it feels much colder than a wooden one, even though they are exactly the same temperature. Your skin measures the rate of heat transfer, not the temperature itself. In this unit, we strip away human perception to define temperature rigorously. This is your gateway into A-level macroscopic thermodynamics, giving you the absolute foundation needed before we can tackle ideal gases or specific heat capacity.
We start by asking what drives heat to move. The answer is a temperature difference. Thermal energy always transfers spontaneously from a region of higher temperature to a region of lower temperature. When two interacting objects reach the exact same temperature, net heat flow stops. We call this state thermal equilibrium. Notice I said net heat flow. At the microscopic level, energy is still exchanging back and forth, but the overall macroscopic transfer is zero. That single word, net, is strictly required by the Cambridge mark scheme to secure your marks.
Next, we need a universal way to measure this equilibrium. Everyday Celsius is fine for the weather, but physics requires a scale that does not rely on the quirks of a specific material, like expanding mercury. This is the thermodynamic, or Kelvin scale. To find the temperature in Kelvin, you take the temperature in degrees Celsius and add 273.15. This fundamental scale starts at absolute zero, the point where a system has its minimum possible internal energy. Remember, a change of 1 Kelvin is exactly equal to a change of 1 degree Celsius. Finally, we look at how to practically build and evaluate a thermometer. You will learn to harness thermometric properties. These are physical traits that change predictably with temperature, such as the electrical resistance of a metal wire or the electromotive force of a thermocouple. You will evaluate these devices based on 3 key criteria: their sensitivity, their range, and their linearity. A classic Paper 4 exam question will ask you to explain why a resistance thermometer and a liquid in glass thermometer, both perfectly calibrated at 0 and 100 degrees, might disagree at 50 degrees. It all comes down to empirical scales and how linearly their properties change.
So, as you tackle this unit, keep your vocabulary precise. You will learn to predict the direction of thermal energy transfer using thermal equilibrium, convert flawlessly between empirical Celsius and the fundamental thermodynamic scale, and select the perfect thermometer for any laboratory or engineering challenge. Let's get started.